Okay, so we'll go back to another video. So here we want to find the antiderivative or the definite integral of the natural log of sine of x plus cosecant square x divided by the natural log of sine of x minus cotangent x dx. So this actually follows up as one of the videos I've done for creating an integral that looks hard, but it's actually easy to compute. If you want to view the first one, the link will be in the description below. So it actually follows a similar procedure from tackling such integral where we're doing it. We actually call a function f of x of our choice, take its derivative, then if we actually just substitute that back into our original integrand, that's everything in terms of f of x, then we can actually do the integration. But however, in this process, when we get to that step, it's actually going to be a little bit tricky, but not exactly tricky, since as long as you know how to apply that creative approach that we're going to apply following up. So with that, once afterwards apply to that, then the rest is history. It'll be simple from there. So why don't we actually just jump right in. So let me call f of x, so of course we're doing our substitution. We'll let that be the natural log of sine of x. Okay, so if I take the derivative, so that means I have, this is going to be 1 divided by sine of x. Then take the derivative of the inside, which is going to be cosine of x. So I have cosine of x divided by sine of x, which we can actually reduce to a nice trigonometric identity of just cotangent x. Then if I take the derivative again, so the second derivative of our originals, so that means that's based on your tables of derivatives to know that f double prime of x, in this case, this is actually going to be negative cosecant square of x. All right, so now that we have all the pieces together, so why don't we actually put everything back in together. So now our new integral, so now everything's in terms of f of x. So that means f of x, and then so plus, so that means that's gonna be minus, so minus f double prime of x, all this being divided by, so f of x, and then minus cotangent, so minus f prime of x, and then dx. So that's what we have so far, but you're thinking, how can we actually easily integrate this? We have a double prime and a prime, but it doesn't look as easily, integrable in this sense that if you applied, say for u-substitution, for example, it's not going to give you exactly what it is that you want. Well, why don't we actually add and subtract a zero term? So that means, in other words, what we're going to do is let's actually add and subtract an f prime of x for our numerator. So I have f of x, so after applying that step, I have f of x and minus f prime of x, then add this with f prime of x, and then subtract f double prime of x, all this being divided by, so f of x, and then subtract f prime of x, and then follow with dx. So now some things can be simplified applying the linearity. So first I have that f of x and minus f prime of x, that will cancel that side out, so it just leaves with an integral of 1 dx. And then all we're left with now is actually just a plus f prime of x minus f double prime. So plus, and then f prime of x, then minus f double prime of x, divided by f of x, and then subtract f prime of x, and then dx. All right, so that's what we're left with. Now it's actually easily, now you can easily see that we can compute this a lot easier. So why don't we actually now apply a u-substitution? So we're gonna let u equals f of x subtract f prime of x. So applying this, that means differentiate both sides. So du is gonna equal to f prime of x, then subtract f double prime of x, then with dx. Substitute this back into over here. So that means now I have, so let me first integrate this. So that means I have x, and then now add this with, so the integral is gonna be just from 1 divided by u du, and then continuing forward from over here. So that means I have x, and then add this with the natural log of, so let me just put in the absolute value for this. So substitute the f of x or the u back into here. So f of x, and then minus f prime of x, and then add this with c. And then afterwards, we can actually just substitute that stuff back in. So now the last step is just x, add this with the natural log of, so f of x, oh, I wrote a parentheses by mistake. So I'm just putting in absolute values just for the sake of that. So f of x, we said that that's going to be the natural log of sine of x, and then minus f prime of x, which is actually just minus cotangent x. And that means minus cotangent x, close that off, and all we're left with is plus c. And so there we have it. That's actually our final antiderivative of our given integral that we want to, well, the antiderivative we wanted to find, the indefinite integral. So it actually comes down to this nice form over here. So actually, while making this integral, I was actually trying my best to find some reasonable bounds that would make sense, in terms of a nice value. So logically speaking, if we're dealing stuff with, trigonometric integrals, you would think bounds such as radians would, properly fit. well, it would work, but however, some places are undefined somewhere in the beginning, so it actually makes it a little bit difficult and tedious to play around with the numbers. So that was the challenging part. So I figured that the antiderivative is actually just best suited enough for that. So that's just, a little bit of banter I just want to put out there. So there you have it. And yeah, that's pretty cool if you ask me.